Hey, I'm Taran, and I've been looking at the performance impact of BGP filtering. So, since that probably means nothing to those of you not into networking, start at the beginning. BGP is the Border Gateway Protocol, and like it's essentially the backbone of the internet. So I'm sure you've heard of IP addresses before. Every computer on the global internet has a single unique IP address, and each internet service provider will have a certain range of IP addresses they're directly connected to. BGP is how different ISPs tell each other what IP addresses they're connected to, so they can work out how to send data longer distances over the internet. Now, while running BGP, it's common practice to apply some filters, and there are a number of reasons for it. It might be like, imagine you have a fancy high-speed fiber link. You might set a filter to hide that from people who haven't paid you for access, because it's expensive to maintain. Or if you have a small ISP connected to a bigger one, you might set a filter to only accept specifically what you expect from the small ISP, so they can't suddenly say, I can get you to Google, because they probably can't handle all that traffic. So in this project, I looked at the action of applying these filters specifically, and tried to work out if and when it has a performance impact, and to try and find possible ways to reduce that impact. So, how does filtering work? Well, the most common type of filtering is address prefix filtering, and these are a sequence of entries all run in order, each having a prefix, pattern, and length, as well as a bit of other metadata that's not too important for this project. So how's prefix matching work? Well, it's kind of in the name. You take your IP address and you write it out in bit format, and then you just check if the prefix matches. So in this case, we're looking at the first 12 bits. In the first example, there's some differences in those first 12, so it does not match. But the second example, the first 12 bits are identical, so the second prefix does match, even though there's some differences later on. Now, how do you test performance? Well, the only real way to do it is just to try it, measure how long it takes, and then extract some statistics. So I created a testing framework to always run the same set of tests to fairly compare stuff. It runs tests in one of two main ways. One's a dedicated program which just applies filters one after the other, doing nothing else as quickly as it can. The other's a more real-world scenario, running actual BGP routing software, which actually receives routes and filters them like it would in the real world, because there's some extra overheads that actually happen there, and it's good to include them in the tests. Now, in both cases, I had some performance monitoring code. I looked through all the results, took some statistics, made some fancy graphs we'll get to later. Now, I also had a ton of separate test cases. Like you can see, I have a total of over 512 varying various different parameters, just to help see how it behaves in different scenarios. Now, as we're trying to find possible performance improvements, it works much the same way. You just kind of need to try it, measure it, and take some statistics, see how long it actually takes. So I created a number of different address prefix filtering implementations. If you're not into computer science, all you really need to know is that they arrange data differently, access differently, and that can affect performance. Now, while running these tests, I ran into a sort of semi-related unexpected result. If I used too many filters, the startup time greatly increased. Nothing to do with applying the filters, just launching tests took a really long time, which turned out to be because it used structured text files for configuration, and it needs to convert that text into binary data before it can be used. When I wrote up some ways to load the filters from binary files instead, with no conversion needed, they ran much, much quicker, like you can see in these graphs. Just point out this is a logarithmic scale. The worst case test took over half an hour, whereas the binary tests are taking just over a second to do the same thing. Now, with that fix, I could run tests reasonably with up to 100,000 filters, and here are the overall results I got. This is the mean of all test cases. Each line here is a combination of 16 different lines. And by looking at those individual lines, I don't have space to fit them, but by looking at them, I could create some insights, more in-depth insights into how to improve performance when designing a new address prefix filtering implementation. But if we're just looking at the overall mean, it's pretty clear that the linked list implementation has by far the worst performance, and the standard implementation has the best. The other thing worth noting here, though, is just on this graph how little the apply time increases. It's only 2 or 3 microseconds, or at worst about twice as long, with 100,000 filters. Since 100,000 is an absurd amount of filters, it's over 10% of the IP addresses that exist in the global internet. In practical real-world scenarios, it's unlikely filtering has a significant performance impact.